Yeah, thanks. I just recently, a few months ago, joined the group of Arno in Berlin. So I have to thank the organizers to bring us all together in this beautiful place. I've been really enjoying my time here, not just the beach and the view, but also learning about all the things that are cooking in this community that is very new to me. But I'm an experimentalist, and I also couldn't help but observe some of these collective effects that everyone is talking about in the wild here. So usually when we're all going back home, we sit together and eat our food alone. And you could imagine when we come all together, this would just be a copy of many of us eating alone next to each other. But in fact, I observed that this is really a very different beast of a collective effect that's happening when we come together and we think together, we work together for a week. And I'm not the first to think about this. And here comes the giants, probably most cited paper of this week. Dicke already thought about collective effects 70 odd years ago. Of course, he wasn't talking about eating together, but he was talking about emitting together. But I hope I can convince you that this is also more than the sum of its scatterers. So you all know that a single atom or a loose connection of atoms will emit its excitation just exponentially over time. And if you bunch a lot of them together and couple them, this looks very different than the atoms emit in a superradiant burst. And luckily, I'm not just standing on Dicke's shoulders, but also on Joachim's and Arno's that already talked about this. And we heard a bunch of beautiful results from Giovanni, for example, about a very similar topic. So I could skip all of the introduction and equations in my slides to go directly to the system that we use, and we check if this system of many coupled atoms still holds in a very peculiar case. So usually when we talk about coupling these emitters, in Dicke's case, that just meant stuffing them so close together that they're closer than the wavelength. And you could, of course, also put atoms in a cavity and couple them that way. But the peculiar way that we like to couple atoms is in a cascaded way, which means that all of our atoms don't just see everyone else. There's no all-to-all interaction, but there's a directional coupling. So the first atom doesn't actually know that there's any others, but the last atom will see the energy and the emission from all the atoms that came before it. So in this particular system, we are interested in checking, does Dicke's prediction still hold? How does this emit? And what are the correlations in this system? So this is what I'm going to guide you through in the next couple of minutes. And I will start with how we build this system. So we need a bunch of atoms. The exact number we will come to. They need to be excited so they can emit, and they need to be coupled to one singular mode. How we do this? Our favorite system is this optical nanofiber. So we build these in-house. We just take a standard optical fiber, we heat it up in the middle, and then we pull it. And when you do this, you end up with, ideally, a nanofiber taper in the middle that is only a couple hundred nanometers in diameter. And importantly, this is small in the wavelength of the light that we're sending through it, while being quite extended over several millimeters longitudinal. Now, when we send light into this fiber, it cannot be supported inside of the nanofiber part of it, but instead is in a guided mode that is mostly evanescent field around this nanofiber. And this gives a very nice opportunity to put atoms, in our case cesium, around this nanofiber and couple them to this evanescent field. If you compare it to just a normal Gaussian mode that you shine on your atoms, you will have many different regions of intensity of your field probed by different atoms, but in our case they all sit roughly 200 nanometers off the surface of this nanofiber, and so they all feel the same amount of light field from this guided evanescent field, and so they all couple very homogeneously with a coupling efficiency of about 1% to this field. Now this coupling, as I already alluded to, is not completely homogeneous, but is actually directional. And this is another effect of this particular nanofiber setup that we use. because when we send in normal linearly polarized light into the normal fiber section of our fiber, when it goes through the taper, this polarization gets squished down and develops a very strong longitudinal component along the nanofiber, which means the evanescent field is actually circularly polarized, so sigma minus. And now we have to look at the fine structure of our cesium atoms. This is the transition that we like to work with, because if we send in sigma minus light, all of these atoms will be pumped closer and closer to the negative MF minus 5 state. And once they're sitting there, they have no choice but to emit sigma minus light. And it doesn't just conserve the polarization, but because they emit the same light that we send in, they also emit it in the same direction that we send in our light originally. So they all of the atoms emit most of their light in the forward direction of our nanofiber. And so this coupling is only going in one direction. The first atom is essentially alone, and the last one receives all of the scattered light that came before it. So this implements this cascaded system, as we call it, of coupling in our atoms coupled to the nanofiber. Okay, now the only thing that is left is we need to excite all the atoms. We send in a pi pulse to invert our ensemble, and then we can look finally what this emission pattern will look like when it comes out. So we prepared our system. We have a bunch, in our case, about 1,000 atoms that are now excited. They're collectively emitting into a singular mode that is guided through our nanofiber, and so we can just connect the output of our fiber into a detector and check how this emission looks. Now, this is a big competition between the normal free space dynamics of the atoms and their collective emission. So, as I mentioned, we only have about 1% of coupling. So usually 99% of the scattered light of the atoms just goes into free space. And this tiny little bit that goes into the fiber is completely dominated by this free space dynamics. So in fact, in the very beginning, when we only have about 100 atoms, this just looks like a bunch of single atom emissions. It's a nice exponential decay over time. Now comes the cool part, of course, when we meet this threshold. So when the number of atoms times their scattering efficiency into our collective mode becomes larger than the free space scattering. So lo and behold, when we have 1% coupling efficiency, if we have more than 100 atoms, this is fulfilled. So as we go further beyond 100 atoms, we see this effect emerging that Dick already predicted. That is a superradiant burst of our emission, where most of the light is emitted in the first few nanoseconds after excitation and then decays way faster than the normal exponential. Okay, so this is the first step that we have observed a superradiant burst even in this cascaded system, which in hindsight seems kind of obvious. It just works the same, but just a few years ago wasn't so clear that it would even work in a cascaded coupling. Now we can come to the part that you've probably been waiting for, which is the whole statistics that we've heard so much about. What is the photon statistics of this burst that comes out of our nanofiber? So when we inverted our system, we used a full pi pulse. And now I'm going to show you a couple of plots where we actually excite with a pulse area that is slightly off of pi. So we can not fully invert our Bloch sphere or all the atoms at the same time. But the idea is still the same. We look at what comes out of our nanofiber. Now we interfered with a local oscillator to boost our signal. And we check the, for now, first order correlations between the excitation laser itself and some time tau within the superradiant burst. So when we start by exciting our ensemble with slightly less than pi, we see a nice oscillation of our local oscillator with our excitation pulse, with our superradiant pulse. And this tells us that this is nicely phase coherent to the excitation laser, which makes sense. If you excite your atoms halfway, they will decay in the same way and pick up the phase over your laser. So if you excite with a bit more than pi, you see the exact same picture, but now with an inverted phase. Okay, they de-excite the other direction. But if we hit exactly a pi pulse and we fully invert the system, now it's like an unstable equilibrium up there, and the pulse that the atoms emit has no correlation left with no phase correlation left with the excitation laser. So at full inversion, this is just a spontaneous decay that sends out the superradiant burst. If we look at many different pulse areas, we can see far away from full inversion, we essentially just have a laser-induced burst, which is completely phase coherent to our excitation. But in a small range around full pi pulse, we can see this visibility vanish, and so we have actually a burst that is induced by vacuum fluctuations and not just the laser. It's no longer coherent. Okay, now that we looked at G1, the logical next step is looking at G2 that we heard already so much about. Same idea, we excite with a pulse area, and now we split our outcoupled light from our superradiant burst, and we measure the G2 correlations for different times within this burst. And just to not confuse anyone, this is a 2-time G2 function. So what you usually know as G2 of tau would be, in my case, a G2 of just the same time twice. This would be a tau of 0, and then of course the time difference between is what we usually put in there as a tau. So this is how it looks, and there's a lot to take in, so let me break it down in small little steps. We of course start in the very initial nanoseconds, so the very initial part of the pulse, and we correlate it with that same time, and we see a G2 of 2, which means initially these atoms just emit randomly like a thermal emitter. But as we again scan our pulse area, we can recover this phase coherence to the excitation laser. If we don't fully invert our system, they just pick up the correlations from the laser, so the G2 goes to a laser like G2 of 1. Okay, the diagonal is probably the most interesting part. So now we still have a G2 of tau 0, but we now scan the time within this pulse where we correlate our photons. And now we start with the exact same data point as before, a G2 at 0 of 2, but as we go further and further down the pulse, this correlation, the second order correlation function, actually trends towards 1 before it then completely drowns in our noise because there's no longer photons coming out of our fiber. But what this means is that originally all the atoms emit randomly, but after a while they actually self-synchronize and they emit a coherent light field, a G2 of 1, without any sort of cavity or gain or feedback on our system. So we have this spontaneous buildup of coherence in our superradiant burst simply by having so many atoms that emit into the same mode and stimulate each other. And finally, of course, this is very similar to what we heard yesterday from Giovanni, and we can now go one step further to a real like 2-time correlations where we correlate 2 different times in the pulse, and we see a bit of a funny picture here. Again, the first point is the exact same data point as before, a G2 of 2, but now as we go on in time, the Dicke model in gray would just predict that this correlation drops because we correlate photons that are emitted very far apart. But what we observe is actually that it goes to 1, below 1, and then rises again. And this is also qualitatively reproducible with a theoretical model that a colleague of mine built up, where we essentially model the system not as 1,000 atoms, that's a bit hard to simulate, but with 1% coupling, but as around 10 atoms with 100% coupling. And even there, we heard just a few talks about this truncated Wigner approximation that he used in this work. And now, how would we interpret this? If I look at this point where I'm correlating an early photon in my burst with a very late one, and this correlation, this G2 correlation is actually below 1, that tells me that it's less likely to detect a photon later in the burst, conditioned on that I already detected one earlier. So our interpretation is that this means that our average burst that we, of course, collect data over many thousands of iterations is just the average, and the individual little bursts are in fact way shorter than that. So if I have this initial this shorter burst here, and I detect a photon here, of course it will have already decayed until I hit this later flank in my emission, and vice versa the same. If I have a lot of emission still left for a burst that emits later, it will not have so many photons in the initial few nanoseconds. But I'm happy to discuss this interpretation. Okay, so yes.
This is for the best pipelines you can do, or do you know your?
Yes, yeah, of course. So this is all for yeah. Sorry, I don't go so far back for the fully inverted system. But I can just quickly summarize, and then we can discuss. So just let me throw the conclusion slide, and we talk. I showed you this this nanofiber platform, which allows us to couple a lot of atoms with at least a decent coupling efficiency to a single optical mode. Makes it very convenient to just plug a detector at the end of your fiber. You have direct access to all the scattering of the atoms. We saw that if you implement this system and excite all the atoms, they in fact do emit a superradiant burst, just as Dicke estimated, but it even remains for this cascaded coupling that we have here, and that the correlations in this burst are quite intriguing, that they actually build up coherence without any sort of feedback. And so we of course could think about some extensions of this, go towards steady state superradiance as has already been done in symmetric systems, look at more initializations that we can think of. And the only thing left for me is to say thank you to all these giants that I work with. So mainly Constanze, who is a wizard in the lab, and Chris before her, of course Arno, who you've already listened to, and on the theory side Felix and Philip, and to thank you all for listening.